Good morning, everybody. Setting up things a little bit differently this morning. I'm going to talk a little bit about some acceleration topics. And then I'll answer any questions you might have had about the learning guide from last day. But let's start with some green check marks so I know you're with me. And then we'll do a couple little, I don't want to call them experiments, but think of them in terms of thought experiments maybe. Exercise your brains first thing. So while you're doing this, we'll have like just a couple minute break here in a couple minutes just so we can fix the studio, and then if you wanted to put any questions in from the learning guide, I'd be happy to do those. So good. Last day we were talking about acceleration, we were talking about change in velocity, and the definition of acceleration is the rate of change in velocity. So if you have your velocity changing from 0 to 10 meters per second, if it changes really fast, that means you have a big acceleration. If it changes really slow, it means you have a lower acceleration. So everything we talked about were cars speeding up, slowing down, people on skateboards, things like that. But what happens if we were to talk about things that are falling? So I have this dry erase marker from my office. If I drop it, what happens to it? What are we saying is going on there? Is the object traveling at a constant speed until it hits the ground? Is it speeding up as it falls? Is it slowing down? How do we describe the motion of something that's falling, an object that's in free fall? And we could talk about its change in velocity as well. The important idea here is that if I drop something, what's its initial velocity? I know I'm throwing a lot of questions at you here. Just trying to get you to think a little bit. So there's some good stuff coming into chat here. Is it speeding up as it falls? Is it a constant speed? Doesn't it go faster, longer because of gravity? These are all the answers I was looking for. So first of all, gravity is what we're talking about. Why does something fall towards Earth? Well, Earth has a gravitational field that's very large, and objects that have large masses will be pulled towards one another because of gravity. So we think of gravity as only existing in, in the scale of like planets and things like that, but everything has a force of gravity. Everything creates a gravitational field. If it has mass, it has a gravitational field. So essentially, me and this pen, we both have a gravitational field. It's really, really small compared to the gravity that's created by Earth, but we do have a gravitational field. And on really big scale, so if you think of the largest things humans kind of can create that move, and like buildings can't move, but super tankers and big boats and harbors, they have so much mass, they're so massive, that if you park two really large boats really close to each other in a harbor, their forces of gravity will actually pull them together. And the force that brings them together is actually really small, but it has been documented. So everything has gravity, but it's just the Earth has a strong, strong sense or force of gravity because it's so large. So what you guys are putting in chat's good. Ava, you asked a question, is it speeding up as it falls? And then Abby also said, doesn't it go faster? Does it speed up, or is it going the same speed? I mean, if I drop that, it's kind of hard to tell in this small little time frame that we have here. But I will tell you this, that anything that's falling towards Earth will continue to accelerate until it hits Earth. We run into a bit of a problem. And if you think about somebody who goes skydiving, does anybody know the word that we refer to that the thing that stops people from continually going faster and faster and faster? Does anybody know what that's called? For objects in free fall? I don't see anyone typing. It's called terminal velocity. So if you were a skydiver, you jump out of the plane and you're flying down towards the ground, you reach terminal velocity, and that means that essentially the force of the air pushing up on you is equaling out to the force of gravity pulling you down, and you can't go any faster. the one really tricky thing that not tricky, the really great thing that we deal with in physics is we ignore air resistance. So for the sake of all the sorts of questions we do, we don't have to worry about the resistance of air pushing up on things. All right, another question that I like to ask is, if I have a sheet of paper here, 2 sheets of paper, if I drop these sheets of paper, what happens? Let's just try it here. They kind of fall down, they move around a little bit. Now, what happens if I take one sheet of paper and leave it like a sheet of paper and take another piece of paper and I crumple it up? These are the same pieces of paper. Now what happens if I drop them both again? What's going to go on here? What do we think? They fall slowly. I like that. What would happen now if I drop them? Happy's getting on the right track. So we're dealing with surface area. Essentially what I've done is I've decreased the surface area of the object. So which one is going to hit the ground first? This is kind of the important thing here. One's more dense, so it'll fall faster. I want to be careful with the word density because it's paper. It has the same density. So I don't think you mean density, but we're talking about surface area. They're identical pieces of paper. They have the same density. The only thing I've changed is the surface area. So I'll drop it, and you guys kind of guessed properly that the paper would fall slower because of air resistance. All right, let's continue that. I have a textbook here, and I have a piece of paper, and they have the same surface area. They're the same shape. They're both 8.5 by 11. So you guys all said, well, surface area makes the crumpled up one fall faster. So if I drop a piece of paper and a book, you've told me that these have the same surface area. Shouldn't they hit the ground at the same time? Taylor's on it. It's heavier. Well, that's an interesting idea. More gravitational pull for things that are heavier. Interesting. I'm not sure. Let's find out. Let's drop these. All right, so the textbook hit the ground first. All right, you said that the textbook was more massive, so it had more weight. It was heavier, so it hit the ground first. And is that the real reason it hits the ground first, or am I just kind of playing with your brains now? What if I can't obviously make this piece of paper weigh the same as this, but what I can do is kind of take away some of the air resistance in the room. Now, I don't have magical powers to suck all the atmosphere out of the room, but what I can do is this. If I drop these and they're side by side, the book's going to fall and hit the ground first. What if I take this piece of paper and I put it on top of the textbook? Like that. Now they are together. What's going to happen if I drop this? Is the piece of paper going to fall more slowly? Or are they going to fall at the same time? Is the paper going to do its waving back and forth as it goes to the ground? You said that the textbook has more weight, so it's going to hit the ground first. Is that going to be true in this case? Shall we try it? See, everyone's feverishly typing. Fall faster because the textbook pushes air away? Maybe. Well, I don't know. Let's find out. So you can see that, I'll do it again, just in case you weren't watching or didn't see it very clearly. If I drop them separately, the textbook falls really fast and the paper kind of floats down. If I put the piece of paper right on top of the textbook, basically what I'm doing is I'm removing air resistance from actually hitting the paper. And if I drop it, I'll drop it again here. You can see that the piece of paper hits the ground at the same time as the book, or it doesn't, float down like it did before. So basically, what I've tried to show you is that the idea is Surface area plays a big role in how fast things fall. But in physics, we ignore surface area. We don't care. It doesn't have any effect on our problems. I shouldn't say it doesn't. We ignore it just to make the problems more straightforward. So then we got to the idea, well, things that are more massive, things that have more weight are going to fall faster. Well, is that the case? No, it's not the case. These have completely different masses. This textbook maybe weighs like, I don't know, 500 grams or so, and this paper, only weighs 1 or 2 grams. But if I put the paper on top of the book, it hits the ground at the same time. So according to our kind of guesses here, things that have more weight fall faster. That's not true. That's not the case. It comes down to air resistance when we drop things. And in physics, all through grade 11, all through grade 12, even through your first year of university, and even through most of second year university, you're going to ignore air resistance. Air resistance is really, really hard to do calculations with, and you have to learn calculus in order to do it. So we just ignore air resistance altogether for objects that are falling. Another important thing here is that these objects aren't falling at a constant speed. They're speeding up. So as they fall, they're going faster and faster and faster because they're accelerating towards the ground. Gravity causes things to accelerate. So if we were to ignore air resistance, imagine a skydiver was falling towards Earth and there was no atmosphere on Earth. Maybe we pick a different thing, like the moon has about 1/3 of the gravity of Earth. If you were to have a magic skydiving plane that could fly to the moon, you jumped off, you would continue to accelerate towards the surface of the moon until you either hit the surface of the moon or maybe you had some sort of fancy rocket ship that slowed you down. So objects will continue to speed up as they fall, and we're going to ignore air resistance altogether for all of our problems. So I'm going to just leave it at that for now. I'm going to put up a few questions here in a second. Why don't you guys just think about them, and we're going to rearrange the studio. And then if you had any problems from the learning guide that you wanted me to go through, you can throw those into chat. And when we come back here in just, like a minute, we can go through those. So throw them into chat. I'm going to put up a few questions. We're going to rearrange everything, and then we will continue on. Thanks. All right, guys, sorry about that. We needed to get my computers and stuff out of the way and the camera, and it's a lot of work. Only one little studio here, we got to make the best of it. Yeah, Abby, either units 9 or 8, anything that came up. I see, Taylor, you've put in a question, so we'll talk about that. And anything, I know, Ava, you had asked about the question. I have it here in the Unit 8 Learning Guide, the last one, from the second half. Number 5, E and F. Those are both fairly tricky questions, so I definitely want to go through those. But first I can do this one for you here, Taylor. So this is page 5, number 13. This is from the Unit 8 Learning Guide. And basically it's asking us to find the average velocity. It's given us a distance and a time. So we went to our formula sheet, we looked at the formula that had average velocity, distance, and time. And we can see that we can just use the information here. The 60 kilometers is a distance, so I'm going to put that on the top. And then we have 3 hours. I'm going to put it on the bottom. 60 divided by 3 is 20, and that is going to be kilometers per hour. Now, we don't have anything in terms of a direction at all, so we can just leave it as 20 kilometers per hour. And that's it. That's all there is to that one, number 13. Unit 8, 7F. 5, 7F. So from the first part, I'm going to assume 5F. Thank you, Eva. The last question. I wasn't finding a 7F. All right, so this is from the graphing motion section of the velocity. And Abby, I'm really sorry that I haven't marked it yet. I usually turn on the notification when students submit it, so I get an email, and I just haven't gone in to look at it or turn it on. So I'll mark it as soon as we're done class here today for sure. All right, so question number 5 is talking about this graph here, and we can see it's a position time graph. We have position up here at the top, time down here at the bottom. So we know that we're dealing with position in meters, time in seconds. Maybe I'll ask you this. Ava, did you get letter E? Did you do that one correctly? Did you get the right answer for E? Because doing the last one is the exact same process. And I guess I kind of alluded to this last day that there's more than one way to think about these problems. There are more than one sort of method to do them to get the right answer. And essentially, it doesn't really matter how you do it as long as you're getting to the right spot. Perfect. Maybe I'll put you on the spot, Ava, and I'll ask you how you did E, and then we'll maybe do the same process for letter F. It just kind of is a bit confusing when we get to F. So for letter F, it asks for the average velocity of the car for the entire trip. And letter E is the average velocity between 0 and 20 seconds. So they're both asking for average velocity. Yep. Perfect. All right. So average velocity formula, V average, is the change in position over a change in time. And because these are both asking us to find the average velocity, we're going to do a change in position over a change in time for both of them. So the first one, letter E, asks us between 0 and 20 seconds. So if I just scroll up to my little chart here, I'm trying to find the average velocity for my graph between 0 and then 20 seconds is right here. So I'm trying to find the average velocity between 0 and 20. So the kind of the highlighted portion there. Now, there are 2 ways I can think of doing this question, and normally the way that I would do it is kind of a really long way, but it's the first thing that kind of pops into my head when I see this. If I want to find the average of anything, I'd add them all up and then divide by how many there were. But in this case, it's a little bit different because I'm dealing with velocities. If you want to think of a trip, I know I used this example before, but if you're driving from here to Vancouver, or let's say from here to like Chilliwack, you drive really slow at the very beginning through Kelowna and West Kelowna. And then when you got on the highway, on the connector, you drive really fast. So if you were doing 10 kilometers an hour and then you're doing 110 kilometers per hour, well, you're not going to add those two and divide by 2. You're going to say, well, I traveled that 10 really for a short amount of time, and then I traveled 110 for a really long amount of time. So when you're finding average velocity, you need to kind of think, well, there was that, a long period of time where I spent at that really high velocity and that really short amount of time I spent at that really low velocity. So how am I going to kind of average those things? Now, you can take how long you spent at each speed and then, kind of think about it in terms of your entire trip. And let's say you traveled half the time at one speed and half the time at the other speed. Well, you could average those out. But that seems kind of confusing here. So what I will suggest is this. When we find the average velocity, we want to take our change in position and divide it by our change in time. So if I draw a little red line, if I found a red line, draw this red line in here, this is the slope between these 2 points. Now, does it matter that my velocity changes between those 2 points? It turns out that it doesn't. And I'm just reading what you have here, Ava. Found the average velocity between 0 and 10, then I found the average velocity between 15 and 20. Didn't really have to find it for 10, 15, so it was 0. And I combined the velocities and got 2. Yeah, so I think that makes sense. I mean, you come up with the right answer, that's a good thing. What I will show you is maybe just kind of a really simple way to do it. And I think this is kind of what Abby was alluding to here. When I have my formula, average velocity is a change in position. So if I have delta D, that's going to be D final minus D initial. It's your change in position divided by your change in time. So let's change my formula a little bit here. df minus di over tf minus ti to make it look like the slope formula, because that's what we're doing. We're finding the slope of this red line that I've drawn up above here. All right, now I'm going to plug in some information that I know. My final distance, if I look at my graph, my final distance, sorry, that's time. My final distance was 40, and my initial was 0. So when I plug these numbers in, my final was 40 meters, my initial was 0 meters, and then time. Well, how long did it take me to do that? It took me 20 seconds was my final time, and this is 0 seconds was my initial time. So I'm going to go 20 seconds minus 0 seconds. So all I've done is I've got these 2 red points. I'm finding the slope essentially between them. I have one point here, this is 0, 0, and I have another point here which is 20, 40. 2 points. And instead of x1, x2, y1, y2, I have t1 or t initial, t final, d initial, d final. So I do this. 40 minus 0 gives me 40 meters on the top. 20 minus 0 gives me 20 seconds on the bottom. 40 divided by 20 is 2 meters per second. And that is how we did that. It is exactly the slope in math, Abby. We've just changed the letters from x's and y's to d's and t's. The important thing is to remember that to find the average velocity from a position time graph, you just need to take the slope. The only thing that makes these two questions a little tricky is because they're asking for different points. And essentially, those points are the same as the points we would have dealt with in math. I've kind of skirted the question of letter F here. I'll talk about that now. So it's asking us for the entire trip. Now, if I go back to my graph here, there was nothing that required this position time graph to start here at the origin and end here. This line could have conceivably stopped here, or it could have stopped here. It was just the way the graph was drawn. It started on the x-axis and it finished on the x-axis. That wasn't by design, it was just kind of by chance. So don't think because this graph starts here and goes up and across and down and back over, it has to end here. That's not the case. The graph could have really ended anywhere. Could have ended here, we could have just ignored this bit. It didn't. It ended and started on the same horizontal line, which does some strange things to our math. Maybe not strange. I'm going to do the same process. It asked for the entire trip, so the trip started here and it finished here. And then I'm going to draw a line from one point to the other. And then I'm going to label my points just like I did before. So this is 0, 0, and this is 0, 45, 55. All right. Now I'm going to plug these into my slope formula. Which is going to look a little bit strange. So we're going to go d final minus d initial over t final minus t initial. And my final distance was 0 meters. My initial distance was 0 meters, or position I should say. My final time was 55 seconds, and my initial time was 0 seconds. So I'm going to end up with 0 meters on the top and 55 seconds on the bottom. Okay, what is 0 divided by 55? Well, that's just going to give me 0. So it turns out that my average velocity over this entire trip was 0. How is that possible? How can we, drive somewhere and taking a trip? How can we just end up with 0 velocity? Does that make any sense? How is it possible that we can end up with that? Because I get this 0 and I'm kind of scratching my head thinking, well, how did it end up with the 0? It doesn't really make sense. I drive somewhere, I'm moving, and how do I just have 0 velocity for the whole trip? I guess the important thing is this. If we look at the trip, it's important to note there's a few things going on here. I have a positive slope here, I have 0 slope here, I have a negative slope here, and then a positive slope here. So velocity does have a lot to do with displacement. In fact, the definition of velocity is your change in position or your displacement divided by the time it took. But one really weird thing about my trip is this. It's not like a regular trip where I just drove somewhere and then I took some turns and things like that. What's going on is the slope of my line is my velocity. So if I look at the first little portion here between 0 and 10 seconds, I have a positive velocity, so I'm moving forward. And then I have this horizontal bit up at the top where I've stopped, I'm not moving. And then I have this really long bit here in the middle where I'm actually moving backwards. I have a negative slope, so I have a negative velocity. So it's not like a regular trip that I'm just driving around, always moving forward. In this example, I have a positive velocity, I have 0 velocity, and I have a large negative velocity, and then a little positive velocity at the end. There's a second way you could have done the problem, and this is kind of what Ava had written up above. I could look at each of these velocities, so I could find the slope of this section, 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 and then I could multiply it by how long I traveled at that, or with a fraction of the entire trip I traveled at that velocity. And I would end up at 0. So I would say, okay, this slope is 6, this is -4, this is 0, and this is, 2. And I'd say, okay, I traveled at 6 for 10 seconds, I traveled at 0 for this long, I traveled at -4 for this long, and I would average them all out, and I would end up with 0 as well. So that's kind of the thing with physics. There's always, not always, almost always more than one way to do these problems. So just kind of whatever makes the most sense to you, just go with it. And Ava, what you wrote up above for the from between 0 and 20 was the same thing. You could have used that same sort of process to find the average velocity over the entire trip. But you could just draw a line connecting your 2 points, find the slope, and that'll also work, because position time graph, you can find the average velocity. Just while we're on the topic, just to kind of, we've looked at this specific example, but maybe extend this question a little bit further. If the question asks, what's the average velocity between 5 seconds and 35 seconds? What I would do is I'd say, okay, 5 seconds is right here. Here's a point. And then 35 seconds is right here. Here's another point. And I would draw a line between my 2 points, and I'd find the slope of that line. Now, it's a negative velocity, it's a negative slope, it's going down and to the right. So that's fine, this process is exactly the same. Just because I don't want you to kind of fixate on this entire trip is 0 average velocity. It's just kind of the way it worked out. So we could ask any 2 time intervals. You're going to find the coordinates essentially. So this is going to be 5, and this looks like at about 30. And then I'd go down here, and this is 35, and that's looking like negative 20. And I would do the same process. Y2 minus y1 over x2 minus x1, or in this case, d2 minus d1 over t2 minus t1, or find the slope. That's the average velocity between those 2 points. So you can do it for any 2 points on the graph. There we go. I didn't see any other questions in terms of the learning guide for Unit 8. Hoping you guys should be done that by the end of the day or tomorrow. Today's Wednesday, I suppose. Should be done this stuff. Test should be written by Friday. That gives you a day to polish this off, and I will start marking those learning guides right away. I want to just jump back into the notes and continue and finish off the Unit 9.1 and then jump into 9.2 for sure, Ava. Number 2 for Unit 9. So this is Unit 9 learning guide. Are we talking about on page 1 here? Make up a sketch of what the pool balls photos would look like if we were accelerating positively and negatively. Yeah, okay. All right, so if the pool ball were to accelerate, that means it's traveling a greater distance in the same time interval. So if I have my pool ball, you can see here it's at very regular intervals. The flash happens. The distances from here to here is the same as the distance from here to here is the same as the distance from here to here. Now, if the object were to accelerate, that means it would travel a greater distance. So what we're going to have to do is space out the balls, make them further apart in the same time interval. So if I have a ball here, and a ball here, and a ball here, those are all kind of the same distances apart, roughly, according to my fantastic drawing skills. Now if it starts to accelerate, I'm going to have a greater distance between each time interval. So these are roughly the same. We'll call them D. That's D. And then this isn't D anymore. It's a little bit larger of a distance, and then it's even larger here, and then it's even larger here again. So that would be an object that would be accelerating. So that's accelerating. The second part of the question asks a negative acceleration, or something that's essentially slowing down. So I'll pick another color here. So if I have my objects that are at regular sort of distance intervals, if the object's slowing down, it's not going to travel as far in the same amount of time. And remember, each time we draw that object or the flash of light develops the film, the object is going to be slowing down, so it won't quite get as far. And then if I were to draw another one, it would look like that. And I eventually would have these things all drawing on top of each other. It's really hard to see that. Space them out a bit more. All right, so there's an equal distance for those things. Then I'm going to draw this one a little bit closer together. And then I'm going to draw this one a little bit closer together. And then I'm going to draw this one a little bit closer together. And then the next one would maybe overlap it a little bit. And then we'd eventually end up with a big jumbled mess where all of the circles are on top of one another as if the object had completely stopped. So that's kind of what we'd end up seeing. There we go. I will jump into the notes and then we'll finish these off. And I hope to get done the course today. I think we'll just fly through this. And if you guys have questions, speak up. If you don't have questions, that's okay. The stuff can get a bit tricky. So some of the problems can get more difficult once you get into the acceleration type questions. So I gave you guys these questions just as we transition. Can the acceleration be positive, but you are slowing down? Can we think of a situation where our acceleration's a positive value, but you're slowing down? How can that happen? This is kind of these confusing things where we start to think of signs. And I guess wrapping your brain around it's kind of the hardest bit. Remember that the sign just indicates direction. So if I have a positive value, then I could say that's forward. If I have a negative value, that's backwards. So I want to think of a scenario where I have a positive acceleration, but my velocity is actually decreasing. Is it possible to encounter that? What if I were walking backwards and I started to slow down going backwards? Would that fit this example? So my acceleration's positive. I'm slowing down going backwards. That means I'm speeding up in a forward direction, if you want to think of it that way. So if I was moving backwards, maybe you're in a car in reverse, you're moving backwards, but then you put your foot on the brake, that means you're accelerating essentially forward, or your change in velocity is going to be positive. So you have a bigger forward acceleration, slow down, but still have a positive acceleration. I'm not completely sure because I find this stuff confusing. It isn't sort of confusing, it's very confusing. So example one, if you're moving backwards and you slowed down, you would have a positive acceleration because your change of velocity would be positive. And then you would be slowing down. Can the acceleration be negative, but you are speeding up? Can we think of an example of a situation where our acceleration's negative, but we're going faster? It doesn't say anything about direction. It says speeding up. So that could be speeding up going backwards, or it can be speeding up going forwards. So example 2, if I was in reverse, that means my velocity is negative. That's fine. And I put my foot on the gas pedal. Is my acceleration negative or positive? Well, because I'm going backwards, and I'm saying everything backwards is negative, so I'm traveling in reverse in my car, put my foot on the gas pedal, I speed up going backwards. Does that fit that situation? Yeah. My acceleration's negative because all negative acceleration means is just opposite acceleration to the direction you're moving. Or I shouldn't say opposite. Everything backwards is negative, not opposite. So if I put my foot on the gas while I'm going backwards, my acceleration's negative because everything backwards is negative, and I'm speeding up at the same time. Car's initial velocity was negative 20, so I'm going backwards at 20. And the car has a positive acceleration of 5. What's the velocity after 10 seconds? That means my velocity is going to increase by 5. Every second. I'm going to jump over to here and let's do this one. All right, so I'm going to draw a car. Here's my car. That's a beautiful looking car. So the car's initial velocity was negative 20 meters per second. So it's going backwards. Hard to tell which is the front of my car and the back, but I'm going backwards at 20. The car is going to accelerate at 5 meters per second squared, or it's going to increase its velocity by 5 every second. 5 meters per second every second. So, okay, let's think of this. We're going to do this kind of two ways. If my car was initially going at negative 20 and 1 second passed, painfully difficult to read that. After 1 second. How fast would my car be going after 1 second? If I started at negative 20 and then I'm saying I have a positive acceleration. That's exactly right, Abby. I'd be going negative 15 meters per second. Okay, what about after 2 seconds? I'm going to develop a bit of a pattern here. So every second I'm changing my velocity by 5. So after 2 seconds, I'm going to change it by another 5. And I'm going to be going negative 10 meters per second. Okay, if I continue this on, what happens after 3 seconds? Well, I'm increasing my velocity by 5. What about 4 seconds? This one's kind of weird. After 4 seconds, my velocity is now 0 meters per second. How is that possible? What does that mean? What's going on? So confusing, Mr. Borden. All right, so we started at negative 20, and we're accelerating forward, but we're moving backwards. That's fine. That just means we're slowing down going backwards. So after 1 second, we're down to 15, 2 seconds, we're down to 10, then negative 5, then 0. What happens after 4 seconds? At 4 seconds, I'm going 0, so I've stopped. But I'm still accelerating going forward. So after 5 seconds, what is my velocity going to be? What happens at 5 seconds? That's right. Now my velocity is going to be 5 meters per second, but it's positive now, and I don't need to write in the positive sign. So what does this look like? Well, I'm moving backwards really fast and I start to slow down. And at 4 seconds, I've stopped, but I'm still speeding up. So I'm moving or accelerating forward. So that's a kind of a way to think about it. And then after 6 seconds, I'm at 10, 7 seconds, I'm at 15. Do I have to do this big, long list of things? No, I can use formulas to figure this out. So if the car has a positive acceleration, what's its velocity 10 seconds later? So I'm trying to find the final velocity, or the velocity at 10 seconds. Okay. Now, I don't necessarily, I know I have all these formulas on the back of my data book, and I need to figure out which ones I need to use. So these are all my equations of motion here. Now, I've just said I'm trying to find the final velocity. And the only formula I have here that's solved for final velocity is, it's just this change in velocity formula that's been rearranged to isolate or solve for VF. So they've just moved VF to this side and V to this side, or delta V, to end up with this VF. So we want to use this formula here. The final velocity is the initial plus the change. So I'm going to jump back over to here. I know my final velocity is my initial velocity plus the change in velocity. Now, I don't know a lot of things, so I'm going to have to use another formula. I know my initial velocity. That's given in the question. It says the initial velocity is 20. So the initial velocity, maybe I'll fit that in here, VI is negative 20 meters per second. Do I know my change in velocity? I don't. I don't know what I changed my velocity over that time interval. But I could find it because I know my acceleration is the change in velocity divided by the change in time. Or, if I jump back over to my formula sheet, what do I know? I know my time, I know my acceleration. I'm trying to find the change in velocity. So essentially this is a two-step type problem. And this is kind of why physics gets confusing. So my change in velocity is my acceleration times my time interval. All right, I don't know what change in velocity is, but I want to find it. My acceleration was positive 5 meters per second squared, and the time that I accelerated for was 10 seconds. So my change in velocity is going to be 50 meters per second. Okay, let's think about it this way. I know my velocity increases, it changes by positive 50 meters per second. If initially I was going backwards at 20, and I know it increases, or my change was positive 50, what should my final velocity be? I can think about it in my head, or I can plug it into my equation up above here. So I don't know what my final velocity was, but I'm going to find it. My initial velocity was negative 20, and I know my change in velocity was 50, because I know I was accelerating at 5 each second. So negative 20 plus 50 is going to be 30 meters per second. So my final velocity is 30 meters per second. Holy cow, Mr. Borden, that was a lot of work for one problem. Yeah, that's about as tricky as they can get, really. It's kind of a two-step sort of process. I can understand why you would get confused, Haley. First time you've seen a problem like this, we'll look at a few more, but it is confusing stuff. We'll look at a few more, and hopefully you'll kind of we'll get it. There's a bunch of problems like this in the learning guide, kind of two-step problems. We'll do more. This is just an introduction to it. So we'll leave that there for a second. I want to jump back into the notes. We'll just polish off the notes here, and then we'll do some more problems like that. All right, so that was this example 3. The next one jumps into acceleration due to gravity, and we talked about this at the very beginning of class. We said gravity's force is pulling between two or more masses, We talked about air resistance as something we just ignore for physics in grade 10 and 11 and 12. Just ignore resistance. You won't see it until second or third year university when you've mastered calculus. So one really common sort of problem, mistake, I guess, that students make is when they look at graphs, they expect the graph to look like the motion of the object. So in this example, this person here is throwing a ball into the air, and the ball is going up, and then it comes back down. Now, if you were to draw a graph of the motion of this object, would you expect it was going to start here at 0, and then it would go up, and then it would come back down? It would look kind of like a parabola, or this shape here. Well, that's what students kind of always assume, that the graph should look like the actual motion of the object, so this kind of horseshoe shape. But that's not what happens. If you think about an object, now before I was dropping the pen and it was falling down and hitting the ground, what if I throw an object up into the air? If I throw it, it rises, and then it stops, and then it comes back down. What's happening to the velocity? Well, let's say the velocity, anything going up is positive. So as I throw the pen up, it's positive velocity. What happens when an object gets to its highest point? What's its velocity? For a fraction of a second at its highest point. And then what happens as it comes back down? What happens to its velocity? So Haley, you're right. When I throw an object up into the air, it has a positive velocity, positive, positive, positive. It's slowing down, positive, positive. And then it's 0 at its highest point. And then it starts to move downwards. And I've said, okay, everything going up is positive. So positive velocity, 0 velocity, negative velocity. Anything going down needs to be negative. So this is what the velocity time graph looks like. I have an object that is slowing down. Although it's moving up, it's getting slower and slower and slower until it stops. And then it starts to fall back down, and it's going to go faster and faster and faster and faster. So this is what your velocity time graph looks like. Your velocity up starts, think about it, the fastest this object's ever going to be going, as soon as I release it, it's going fast, and then it starts slowing down. Gravity's pulling it down, it starts to slow down, it stops, and then it starts to speed up going downwards. So my velocity slows, 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 gets to its highest point. This is its peak. The velocity is going to be 0. And then it's going to start falling down. So it's going to have a negative velocity. Now, this number, 9.8 meters per second squared, is the acceleration due to gravity on Earth's surface. This is, in physics, what we call a constant. And this number, for Science 10, you need to memorize. Now, I've said this before, oh, I don't like you guys to memorize stuff. Unfortunately, it's just one of those things. The good news is you're going to use it so many times that it's going to be just like second nature. The acceleration due to gravity on Earth's surface is 9.8 meters per second squared downward. So you'll get really good at using this number. Anything, an object's dropped, an object's thrown, an object's falling, you know the acceleration. You know it. It's negative 9.8 or 9.8 meters per second squared. In the problems, kind of really commonplace students will make mistakes is they'll get to a problem and it won't tell you the acceleration. But as soon as you know an object's being thrown, dropped, shot, I guess there's other situations, but those kind of big three, thrown, dropped, are the big ones. You know that the acceleration is going to be 9.8. It's an object in free fall. It's not being held. It's not rolling down a hill. There you go. So here we go. We have an example of a rock falling off a cliff. What is the change in velocity of the rock after it has fallen for 1.5 seconds? And then this problem actually tells us everything that's going down needs to be negative. So let's see if we can do this example. All right, So I'm gonna draw a little picture because I love my pictures. There's my cliff. Guess my cliff doesn't even need to have a bottom. I have an object that's falling off the top of a cliff. And I want to know the change in velocity when the time is 1.5 seconds. Good question, Abby. If something is being thrown into the air, isn't the upward acceleration depend on how hard you throw it? That's true, but there's a limitation to what you've said here. If I am throwing this pen up into the air, I can throw it really hard and it'll go really high. But the second my hand loses contact with the pen, I'm no longer applying a force to this pen. I'm no longer pushing it. So the second the pen leaves my hand, it starts slowing down. Gravity's pulling it down. It slows down, slows down, slows down until it comes to its highest point, stops, and then it comes back down. So yes, what you've said is kind of difficult to understand, but anytime something's thrown into the air, it doesn't matter how hard I throw it, soon as it leaves my hand, it starts slowing down. If that weren't the case, if it continued to speed up after it left my hand, then, you know, throwing things into the air, launching satellites into orbit would be really easy. Because as soon as you let go of it, if it still kept speeding up, we could just get it right into orbit and it'd be just, everyone could go home. It'd be really easy. But we stop applying a force to it, we stop pushing it the second it leaves your hand. And starts slowing down. Same thing goes, think about the opposite. If I throw this object down, and as soon as I let go of it, that's a point where I've stopped applying a force, and that's its initial velocity. And then it's going to speed up going downwards because gravity is going to pull it down. So maybe you're getting the two mixed up. Acceleration is always the same, negative 9.8 or 9.8 down. And just the idea here is as soon as you let go of it, it's going to stop. It's not going to go any faster. As soon as you let go of it, it's going to slow down if you're throwing it up. Pardon me. So what's the change of velocity after it's fallen for 1.5 seconds? I look at the question, I only see kind of two pieces of information. I have a time, 1.5 seconds. I have that's it, essentially. I'm asked to find change in velocity, so I only have these two things. Now, this is where students get confused because they're like, Mr. Borden, I have formulas with 3 things in them. I only know 1, I only know 1.5. What else do I have, or how am I supposed to find this? Well, as soon as we see the word fall, thrown, drops, these are all indicating that an object's in free fall. So as soon as I see that, I know my acceleration is going to be negative 9.8 meters per second squared. Now, why is it negative? Acceleration due to gravity is going to pull things down. And I've said at the very beginning of my physics unit, anything that's going down is going to be negative. So acceleration due to gravity is pulling things down. It needs to be negative. Shouldn't really make much of a difference. It's just a direction. I could do the same problem with everything being down positive. It doesn't much matter. I'm asked to find my change in velocity. So what do you know? I'm already on that. Change of velocity is going to be my acceleration times my time. It's already solved for me on the back of my formula sheet. So I'm going to use that formula. Change in velocity is the acceleration multiplied by the change in time. Or I could just go acceleration times time. All right, change in velocity, my acceleration is negative 9.8 meters per second squared, and my time is 1.5 seconds. So this isn't going to be a nice mathematical thing. 9.8 times 1.5, it's going to give me a decimal. That's okay. change in velocity is going to be negative 14.7, and it's a velocity. So I end up with meters per second. Okay, that's all we need to do. Just ask for a change in velocity. I have this negative sign, just means down. How do I know which one to use? That's a really good question, Taylor. So in my problem, I need to figure out which variable I'm trying to find. So if I read the question again really carefully, the question is asking me to find what is the change in velocity. If I ignore everything else, I see that one thing, it's asking me to find a change in velocity. And I know a change in velocity is change is delta and then velocity is v. So that's what I'm looking for. So I need to find this guy. So if I go to my data booklet, doesn't look like this, looks like that. I need to find a change in velocity. So it turns out that change in velocity appears twice. Right here I have change in velocity, and here I have change in velocity. Well, what other information am I given in the question? In the question I'm given a time, so I know that, and that's the only other thing I know. I suppose I know acceleration because it's falling, so it's negative 9.8. I don't know final velocity, and I don't know initial. I do know initial, it's 0. So I can't use this formula because I don't know the final velocity. So I want to get rid of that. I can use this one because I know both the acceleration and the time. So that is why I have chosen this guy right here, because I'm asked to find the change and I know the other two pieces of information, the acceleration and the time. So on a very basic level in physics, if you want to just think about it in terms of equations, you can. There's nothing wrong with that. It's important to kind of try to understand what's going on, but sometimes it's easier to just forget about what's going on, figure out what you're trying to find, figure out what you know, and just use a formula that can find the thing you want to find based on the things you know. I'm going to talk about these, we'll talk about Galileo, and I'll look at a couple of videos, and then we'll take a quick break and we'll come back and we'll finish off this stuff. So there's a famous story about a scientist named Galileo. Galileo Galilei was his name. It's kind of a silly name if you ask me, but his parents liked it, so we'll go with it. Who am I to make fun of names? So Galileo was a famous scientist, and he went to the top of the Leaning Tower of Pisa, and one of the top balconies, and he had two stones. So this is kind of what I was doing at the beginning. So he had these two stones. One was really big, and one was really small. And he went up to the top, and he dropped these two stones, and he looked at what happened. So the assumption that everyone would have made, and I guess some of you probably did at the beginning of class, is the thing that's heavier should hit the ground first. But it turns out that mass has no bearing on how fast things fall. It doesn't matter if you're extremely massive or have a very small amount of mass or really big or small. The weight of an object doesn't matter once it's in free fall, which is kind of a really strange sort of thing that happens because of physics. So the crowd was amazed because both of the rocks hit the ground at the same time. Again, a really small rock, really massive rock, if you drop them, they'll hit the ground at the same time. Just like before when I had a piece of paper and a textbook, they had different masses, but if I put the paper on the textbook, they hit the ground at the same time. So every object will accelerate towards the surface of Earth at 9.8 meters per second squared. You end up memorizing this kind of formula. So if you drop the objects from rest, so their initial velocity is 0, after 1 second, how fast are the rocks falling? Well, if Every object near the Earth's surface accelerates at 9.8 meters per second squared. That means after 1 second, it's going 9.8. After 2 seconds, it's going 9.8 times 2. Let's do that on my calculator, 9.8 times 2. 19.6. After 3 seconds, it's going 29.4, and objects will accelerate like this towards the surface of the Earth. Now, scientists, had no way of, I shouldn't say had no way, they were amazed that these objects had different masses and they felt the same, they hit the ground at the same time. It wasn't until I don't even know the year the experiment happened, around 1969, where we could actually take Galileo's idea that objects with different masses fall at the same rate, and we could actually test it somewhere. And does anyone know the significance of 1969? What happened in 1969? Pretty famous thing. Mr. Ross knows. Mr. Ross, what happened in 1969?
Moon landing.
We landed on the moon. What's special about the moon? Well, the moon doesn't have an atmosphere. There's no air on the moon. You can't breathe on the moon. There's no atmosphere there. So what happened in 1969 was, this is a really not an amazing video of it, not really great quality, because, well, it's taken on the moon and in 1969. But one of the astronauts, I forget his name, I apologize to the nice astronaut. One of the astronauts took to the moon a hammer and a feather. Literally took these to the moon, and we did an experiment on the moon with a camera watching, dropped a feather and a hammer at the same time. Now, we've discussed this a little bit already, but what should happen to the hammer and the feather? I think my favorite part of the video is when the guy wearing like the NASA shirt, some guy who works for NASA, one of the smartest people in the world, probably, he's just amazed by this result. Like, that's how cool that is, that you can actually do that. So there you go. Objects will fall at the same rate. They'll accelerate towards Earth at the same rate, regardless of how much they weigh. The only thing that's important in this case is air resistance. So really cool that they did that experiment, and you can actually see that the feathers don't even really move. I mean, initially they kind of flinch a little bit. That's, object at rest tends to stay at rest, and then once it starts moving. But yeah, if you remove air resistance, some pretty amazing things can happen. So they did it in 1969 on the moon, but they didn't have high definition cameras or anything like that. And then they could, of course, do it in this place in Cleveland. One thing that I want to kind of point out about the video is that they slowed it down. It's not like the objects were falling really slowly, it's in slow motion. So they kind of slowed it down so you could see that the feathers weren't moving and the ball was falling at the same sort of rate. But if they showed it in real time, the objects, the feathers and the bowling ball would fall like they would normally fall, or you'd be used to seeing them fall. So there you go. That is things falling without air resistance. What I'll do is this. I will leave you guys with these 3 questions, and I want to take we'll go a little 10-minute break so you guys can get up, move around, and get some snacks and drinks. And we'll come back, we'll look at these questions, and we'll get to the last section, and we'll finish off this course. So maybe 10 minutes. You guys can have a little breather, and we'll come back, and if you're kind of bored during the 10 minutes, you can do these 3 problems. Thanks. Hi guys, welcome back. If we can start with some green check marks just to make sure everything's running. I'll go through these problems and then we'll finish off things. Kind of push to get everything done. Have about an hour. Hopefully we can get this done in an hour. All right, example 1, if you consider up to be positive, what is the acceleration due to gravity of a dropped stone? So up, positive, if you're dropping a stone, we're talking about the acceleration, it's going to be negative 9.8 meters per second squared. If you throw a rock up into the air, when its velocity is 0, when is the velocity 0? What is the acceleration when the velocity is 0? This is a really great question, example number 2, to kind of get it straight in your mind, the difference between velocity and acceleration. So if I throw a rock up in the air, a pen, whatever, when is the velocity 0? So I think Haley and Anna both wrote this in a bit earlier. When it gets to its highest point, its velocity is going to be 0. What is the acceleration when the velocity is 0 though? When an object gets to its highest point, when you throw something in the air, what is the acceleration at its highest point? So your velocity is 0, we've established that, it goes up, it stops, and then it comes back down. But at its highest point, what is the acceleration? So throw that into chat, enlighten us as to what the acceleration is going to be. And while you're doing that, a stone is dropped from a cliff. What is the velocity after 1 second and after 2 seconds? So, example number 2. An object is in free fall. It doesn't matter if it's going up. It doesn't matter if it's going down. It doesn't matter if you shot a bullet out of a gun or a cannonball out of a cannon. As soon as the object leaves your hand, leaves the gun, leaves the cannon, the object starts falling towards Earth at negative 9.8 meters per second. Does it matter if I, throw an object up or sideways or down? No. It doesn't matter the direction you launch an object, throw an object, drop an object. As soon as it leaves your hand, doesn't matter if it's going up, down, sideways, front, back, it starts accelerating towards the center of the Earth at 9.8 meters per second. So even though I've thrown an object up into the air, it's still accelerating downwards, even though it's not moving downwards. This is kind of one of the difficult ideas behind acceleration. Your acceleration can be down, even though your object's moving up. Just like if you're in a car, and you're moving forward, my velocity is forward, it's positive. If I slow down, my acceleration's backwards. My acceleration, my change in velocity is going to be negative. If it was positive, that means I would be speeding up. So it doesn't matter what an object's doing. If it is in free fall, it is accelerating down, or has a negative acceleration, an acceleration of negative 9.8 meters per second. Doesn't mean it's moving down, it means its acceleration's down towards the center of the Earth. So this is one of these really kind of weird things, not necessarily weird, but kind of difficult ideas to kind of wrap your head around. When it isn't moving, how can the acceleration be down? Okay, let's go back here. This was the velocity time graph of the object thrown up into the air. Now, it turns out that we haven't got this far, but the slope of a velocity time graph is actually the acceleration of the object. Now, even though right here, where the object is traveling at 0 velocity, it's at its highest point, right, when it crosses this x-axis, it is still accelerating downward. Its change in velocity, maybe that's kind of where we're getting caught up. Acceleration is your change in velocity divided by how long it takes the velocity to change. So if your object's falling, your velocity is changing. It's as fast as it's ever going to go as soon as you leave your hand, slowing down, slowing down, slowing down, slowing down, 0, and then it starts accelerating down, going faster and faster and faster, negative. So your velocity is changing, and your velocity changes different than the direction it's moving. This is why acceleration is kind of difficult to wrap your brain around, I suppose. So we watched the moon, we watched this feather and this giant chamber. A couple of really other cool things from this video. I could just talk about this video all day, but in that giant chamber, there's 3 tons of air. Right now, you have literally thousands and thousands of kilograms of air pushing down on you, but you're just used to it because you're born into it. It's just normal. Crazy things happen in vacuum chambers. I don't have time to talk about them all. Stone is dropped from a cliff. What's its velocity after 1 second? Mr. Borden, I don't know how much the stone weighs. I don't know how high the cliff is. How am I going to find out anything about this stone? It's dropped off a cliff. It's so confusing. It doesn't matter. It doesn't matter how much the object weighs. We've shown that in the vacuum chamber. You can have a feather, you can have a bowling ball. They're going to fall at the same rate. So if it's dropped, it means its initial velocity is 0. So your initial velocity is 0. And after 1 second, it's increased, it's accelerated at 9.8 meters per second squared. That's right, Anna. But one thing that I want you to be very careful with, Anna, is that the units for velocity and acceleration are different. So if I'm asking you the velocity after 1 second, it's negative 9.8 meters per second. Its acceleration is negative 9.8 meters per second squared, which is fine. But its velocity is negative 9.8 meters per second. And then if we take 9.8 and multiply it by 2, we get 19.6. So after 2 seconds, it's at 19 or negative 19.6. The acceleration is still negative 9.8, but it's increased its velocity. It's changed its velocity by 9.8 meters per second in that additional second. So 9.8 in the first second, 19.6 in the second. It's going down. We'll call it negative. There you go. What is the change velocity for a brick that falls for 3.5 seconds? The ball is thrown straight up in the air. How long does it take for the ball to slow down to 6? Let's do these examples in OneNote. All right. So change in velocity of a brick that falls for 3.5 seconds. Now we've already done a question really similar to this. Change in velocity is delta V, and this is what I'm trying to find. A brick that falls for 3.5 seconds, so I have a time is 3.5 seconds, and it's falling, so my acceleration is negative 9.8 meters per second squared. So those are the 3 things I know. This comes back to the question that you asked before, Taylor. You said, how do I know which formula to use? Well, if you want to think just in terms of these formulas, I'm asked to find a change in velocity, I have a time, and I have an acceleration. These are the 3 things I know. So I need a formula with these 3 things in them, delta V, T, and A. And I need to find one that has delta V already solved, because that is the thing I have been asked to find. So I go to my data booklet, I see that delta V is my acceleration times a change in time. So I can take my acceleration, negative 9.8 meters per second squared. I can multiply it by time, 3.5 seconds. And unfortunately, I have to put that into my calculator. 9.8 times 3.5 is negative 34.3 meters per second. So that means it's going to be traveling 34.3 meters per second, going down after 3.5 seconds. All right, example number 5, or the second one on this page. A ball's thrown straight up into the air. When the second it leaves your hand, it's traveling at 14 meters per second. It's going to slow down till it reaches its highest point. And the question asks specifically, how long does it take the ball to slow down to an upward velocity, a positive velocity of 6? So we're going to look at the question, figure out what we know, what we don't know, and what we're trying to find. So a ball is thrown straight up into the air at 14 meters per second. That is an initial velocity, or VI. That is the starting speed. how long to slow down to an upward velocity of 6? So that's going to be my final velocity. It's slowing down to 6. My initial velocity is 14. It slows down, slows down, slows down. Now it's going 6. The question is also asking for how long does it take? So that means I am trying to find a time. So I have initial velocity, I have a final velocity. I'm trying to find time, and because my ball is thrown into the air, I know my acceleration is negative 9.8 meters per second squared. As soon as I see something thrown, dropped, fired, launched, as soon as it's in free fall, I know my acceleration. Turns out that this is going to be a two-step type of question. I'm trying to find time, and I'm given acceleration and 2 velocities. So what I can do is say, okay, a change in velocity from my formula sheet is the final velocity minus the initial velocity. A change in anything is the final minus the initial. So the final is going to be 6, and the initial was 14. So my change in velocity is going to be negative 8 meters per second. On my formula sheet, I'm trying to find time, and I know the acceleration, and I know the change in velocity. So time is change in velocity divided by the acceleration. That's the formula I'm going to use. Because it's solved for time, the question asks, how long does it take? So time is change in velocity divided by my acceleration. I know my change in velocity because I just calculated it, negative 8 meters per second, and my acceleration is negative 9.8 meters per second squared. One kind of interesting thing that comes about here is if you make a mistake with one of your signs, you end up with a negative time, which would be really cool to be able to go back in time, but not very practical in terms of calculations. So the time would be negative 8 divided by 9.8 is 0.816, so 82 seconds. So you throw something up at 14 meters per second. After 0.82 seconds, it's going 6 meters per second. Let's do this last one. Rock is thrown downwards, initial velocity of 8. What is the velocity after 1.5 seconds? So again, let's look at the question. Initial velocity, 8 meters per second. What is the velocity, which is going to be my final velocity, is what I'm trying to find. I'm given this 1.5 seconds, and I know my object's in free fall, it's thrown, so my acceleration is negative 9.8 meters per second squared. All right, so I know from my formula sheet that final velocity, which is what I'm trying to find, is the initial velocity plus the change in velocity. So let's go back. V final is my initial velocity plus my change in velocity. Now my initial velocity is 8. But I don't know my change in velocity. Can I find my change in velocity? Better yet, how can I find my change in velocity? That's what I need to find in order to find out what the final velocity is. Is there a way I can find a change in velocity with the information I'm given in the question? Let's go back to our formula sheet. Change in velocity. I have a change in velocity right here. Acceleration times the time. Does that work? Do I know the acceleration? Sure do. Negative 9.8. Do I know the time? Yep, that was given in the question. So I can go back to my formula sheet and say, okay, I need to find the change in velocity in order to find the final velocity. So I'm going to use change in velocity as my acceleration times my time. So I'm trying to find change in velocity. It's my acceleration times my time. Negative 9.8 meters per second. Time 1.5 seconds. Negative 9.8 times 1.5, negative 14.7 meters per second. That negative sign is super duper important. Don't drop it. You'll end up with the wrong answer. So the signs are important. I had a negative acceleration. Everything down is negative. The time's positive because we can't have a negative time. So this delta V here, my change in velocity, I can put into my formula. Negative 14.7 meters per second. So 8 plus negative 14.7 negative 6.7 meters per second. I fear I've made a mistake. That doesn't sound right to me. Acceleration is negative 9.8. My initial velocity is 8. Oh, can you guys see the mistake I made? It's really easy to fix, but I've got the wrong answer. Why did I know I got the wrong answer? Because if you could imagine something being thrown at 8, if I throw something down at 8, it's going to speed up as it falls. So if I wait 1.5 seconds, its velocity is not going to be negative 6.7. That means it was slowing down. Because it started at 8, now it's only going 6.7. So I made a sign error, which is an important lesson for me and you, I suppose. Where's my sign error? The math is right, Abby and everyone else. The math that we've done is right, but we've made one terrible mistake. It's like the question set us up for failure. I'm going to get rid of this 6.7 because it's wrong. Nobody can see it? You guys are probably just glazed over with all of this stuff right now. Right here. My initial velocity is 8. Can anyone see it now? What's wrong with that 8? The 9.8 is negative. I'm happy with 9.8 being negative going down. That's good. If I say in my question, everything down is negative, what's wrong with this 8 meters per second here? What was important about it initially? The object was being thrown downwards. If my initial velocity was down, this 8 should be negative. Alex, you're on it. Brought your A game today, Alex. Thank you. So this is my mistake here. I needed to put a negative 8 in here. This should be negative 8. Now, I wish I was smart enough to go back and say, well, I made this mistake so you guys would pick up on it and see it, but I was actually an honest mistake. So it was initially going negative 8, and then it increased by 14.7 in a negative manner. So now it's going down at negative 22.7, which I am much more happy with. So I guess the lesson here is Be careful with your signs. And does your answer make sense? It's also a good little question to ask when you get to the end of this sort of thing. All right. I think that's it for 9.1. Yeah. There's something in the course about how many G's can you handle. It's about like fighter jet pilots and accelerations that they feel when they're flying their planes, because they're changing their velocity really quickly by going around corners and speeding up and slowing down. You might have heard the term before, oh, he was pulling 5 G's or 6 G's. So G is the acceleration due to gravity, is negative 9.8 meters per second. If we talk about how many G's something is pulling, it just means how many more times the force of gravity is that person experiencing. So if you're in a car or a roller coaster, basically your body can handle so many G's, and astronauts and fighter pilots get training because they go through an amazing amount of force and acceleration when they launch in space or they're fighting in their planes. So 1 G is the acceleration due to gravity. That's what I'm experiencing and you're experiencing right now, sitting on your chair and standing here on Earth. 2 G's means just they're accelerating at twice the acceleration due to gravity, so 19.6. 3 G's would be 3 times 9.8. 4 G's is 4 times 9.8. So most humans can handle, I think it's between 4 to 6 G's. And then once you get past 6 G's, basically the blood doesn't get pumped around your body and you just pass out, you black out due to lack of blood flow to your brain. So yeah, in the like 4 to 6 G range, you can do some training and things. It shows you in the video to basically squeeze the leg muscles, forces the blood back into your torso and to your brain. What if there was an object that couldn't be accelerated? That's a great question, Alex. What if? What if? I don't know. What do you think? What's my son? He's 3. He asks a lot of what if questions, and I always throw them back at him. So I'm gonna do that with you, Alex. What if? What would you think would happen if an object couldn't be accelerated? How does gravity affect you in the ocean? That's a pretty interesting question, actually. Have you ever seen, maybe Ava, when astronauts are training to go to space, because we can't simulate lack of gravity on Earth, we put astronauts in pools. And astronauts do training in pools because it's a great simulation for weightlessness. You've probably experienced this before if you've gone swimming. You can, if you stay really still, you can lie on your back and you can just float, or if you're underwater, you can float and just not move. Well, what's happening is when you're underwater, the reason things float on the water is because of buoyancy. And you've probably talked about buoyancy in grade 9, I think you talk about it. So basically, buoyancy is a force that, because you've displaced water, you have a buoyant force pushing you up. Now, for astronauts and things that are training underwater, what they do is they take the spacesuits, which are going to displace water, which makes them want to float, and then they put weights on them so they sink. And if the amount of buoyant force equals the force of gravity underwater, then the object is buoyantly neutral, so it kind of just floats. It feels like weightlessness. And this is, the same weightlessness you'd feel if you were to, be floating around in space and things like that, in orbit. Same idea. So that's why they train underwater, because the buoyant force is the same as the force of gravity, and you experience weightlessness. Do you know if gravity is stronger at the bottom of the ocean? Yes. Gravity is different. So Earth's gravity is different depending on where you are on Earth. So right now we're 300 meters-ish above sea level, and the gravity that we experience is just slightly less. I think it's about 9.78 meters per second squared, because we're further away from the center of the Earth. If you were to go to the bottom of the ocean, you would be, several kilometers closer to the center of the Earth, and the force of gravity would be slightly bigger, maybe like 10 meters per second squared instead of 9.8. You go to the top of Mount Everest, it's 8 kilometers away from the surface of the Earth. Your force of gravity would be smaller, like 9.7 something meters per second squared. So the fact that gravity is stronger at the bottom of the ocean doesn't mean anything because you're underwater, but just because you're closer to the center of the Earth. So the distance you are away from the center of the Earth affects your gravity. How fast is terminal velocity? Sorry, getting back to your question. Alex, terminal velocity depends on lots of things like how much air resistance you have, your surface area, and things of that nature. So a piece of paper's terminal velocity is, we watch that paper kind of float down. If I dropped a penny, it would have a different terminal velocity. So terminal velocity is a function of how much surface area you have. When you see skydivers, they jump out of a plane, they do this kind of like starfish thing so they can control their descent. And then if you've ever seen like action movies where the skydivers do this like tuck and they put their arms down and they do this kind of like thing and they speed up all of a sudden. You have a big surface area like this, you have a small surface area if you tuck your arms in. So a human can have a different terminal velocity depending on what their shape is. So terminal velocity is just basically when the air resistance kind of equals out with the force of gravity. That's when you reach your terminal velocity. Water pressure and gravity have a relationship. Yes, but not the way you're thinking, Ava. Water pressure and gravity have a relationship because they're both forces. So not water pressure, but buoyancy. Buoyancy is a force and gravity is a force. So we can compare them just like we can compare the force of magnets. Magnetic force, that's a force. So a force is anything that's a push or a pull. So because buoyancy pushes you up, gravity is pulling you down, those are forces, and we can calculate the total force of an object. We could put a magnet next to an astronaut or below them, and the metal in their suit would be sucked down, and then we'd have to give them more buoyancy, displace more water until they kind of got that weightlessness. So just getting to the idea of forces in general. So a baby would fall faster than a sumo wrestler because the baby has a smaller surface area. Yes. I don't know why we're thinking about babies and sumo wrestlers skydiving or falling, but that is true. I don't know if fall faster is a word I would use. I would say something like, you don't want to use the word fall faster because it's implying that the acceleration is different. We're talking about terminal velocity. So a baby would have a higher terminal velocity, would be faster than a sumo wrestler just because they have a smaller surface area for sure. Could you jump slightly higher at higher altitudes? Yes. Just like if you've ever seen footage of people walking on the moon, the acceleration due to gravity on the moon is about 3 meters per second squared instead of 9.8 like on Earth because the moon's much smaller than Earth. And you can see the astronauts kind of bounding around and it kind of looks like they're walking on a trampoline just because the force of gravity is a lot smaller. So you could run and jump and you could, go a lot further on the moon than you could. Or if you've ever seen a movie like, what was the movie? Armageddon? I think they're on like an asteroid, and Armageddon did a famously bad job of the physics of being on an asteroid. Asteroids are very small, wouldn't have a very strong force of gravity, but they're all kind of driving around and walking on the surface of this asteroid like it's just nothing. So there you go. On a plane, well, you could do a calculation. Take Physics 11, you could do that exact calculation. You love that movie. How come the moon hasn't smashed into the Earth from Earth's gravity pulling the moon? Because the moon is in orbit. So it's not falling. If we stop the moon, it would fall into Earth and that would be bad. But the moon's actually in orbit. Just like, this is completely off topic, but this is the most misunderstood concept by the general population in terms of space, in my opinion. Astronauts in space, they're in space. They're above the surface of the Earth. Let's say they're 100 kilometers above the surface of the Earth. Well, they're above the surface of the Earth. They should feel the gravity of Earth. Why don't they? Well, they do, but they're in orbit. So they're constantly falling towards the surface of Earth, but in a circle. So they never reach the surface of Earth. So astronauts, if you were on the International Space Station and you could stop the International Space Station, so stop it from moving and just kind of hover it above the surface of the Earth, the people in the space station would feel gravity. They could walk around. But because the object, the space station, is constantly falling towards the surface of the Earth, it's in orbit, they feel weightless. Just like if you were to be taken up to in a plane, and I put you in an elevator and I push the elevator out of the plane, you would feel weightlessness. You couldn't see out, you couldn't see you were falling, but you would feel weightless until the elevator hit the ground. Now, if you're in the plane and you're in an elevator, the plane's holding you in the air through the buoyant force of the wings in the air, but you could stand on the bottom of the elevator and you'd feel the force of gravity in a plane. That's normal. But if you throw the elevator out of the plane, it starts free falling, you'd be weightless until you hit the surface of the Earth. So this is how they simulate gravity on space stations in orbit. Now I'm getting really, really off topic. That's okay, it's okay. We're almost done the course. How do they simulate gravity on space stations in orbit? Our space station doesn't have any gravity simulation. What we could do would be to make a big kind of revolving ring. If you've seen the movie The Martian, their Mars orbiter thing has a big ring that spins. And because it's spinning, it causes something called centripetal force. And that causes you to be able to, walk around. When the astronauts train to go into outer space, they take a 747 or a 737, a big jet. They take all the seats out of the inside of it, and the jet flies up into the air, and then it dives back down. And it's called the vomit comet. And as the plane gets to its highest point, you get weightlessness, and then it kind of free falls. So it accelerates downwards at 9.8 meters per second, so the astronauts feel weightless. And you can go on the vomit comet, and you can feel weightlessness for short periods of time. So the plane just constantly does big parabolic arcs. And you get to the top, you feel weightlessness, the plane accelerates down at 9.8, you get weightlessness, and then you get gravity again, and then weightlessness and gravity, and you just keep doing that. Could they put magnets in their shoes? Magnetic force is much weaker than the force of gravity. It's relatively a weaker force. So the force of gravity isn't as much stronger than magnets. Magnets work in space. Yes, they do. Magnets work everywhere. All right. Well, that was a good waste of 10 minutes. Not a waste. Very important 10 minutes discussing topics related to science, astronauts, things like that. I said I'd do some more of those two-step problems, but what I want to do is finish the course. You see, 9.2, also known as the end. So this is the end of the course. Ava, I've taught Physics 11 a bunch of times, and these are all kind of Physics 11 type concepts. And when you find stuff interesting, you just remember it. It's just kind of cool stuff. Students always ask the same sorts of questions, so you get used to answering the same sorts of things. Now you know, and you'll remember it, and you can talk about it. People that are interested in sorts of stuff. So what I'm going to do is I'm going to power through 9.2. Got about 20 or so minutes to get through it. And then we are going to, Alex, there's lots of science left. What we're going to do is we're going to get through 9.2. That's the end of the new material. So today is the last course for this, or last class for this week. Next week we'll have class on Tuesday. Wednesday we're going to go to KSS and do a lab at KSS. Very excited about. And then we're going to just continue, next class we'll go over any information from chapter 9 that you had questions about. And then I'll start reviewing for the final. We'll start going through the practice exam. And I have some big review packages that we can go through for each unit. So I have a chemistry review, I have a biology review, I have an earth science review, and some practice exams to look at. So we've got lots of things left, but this is the end of the new material. All right, so I'm going to power through this. 20 minutes, and then we'll go over all the questions you might have next day, and then we'll start review next day. So, we've already talked about acceleration. The only thing new in this section is we're going to deal with some velocity time graphs. Do we have a final? I haven't decided if I want you guys to write a practice final or not. You guys definitely have the provincial for sure, but I'm kind of on the fence about a practice final. So we might do it, we might not. We'll see how I feel next week. So acceleration depends on the change in velocity. The smaller amount of time the change in velocity happens, the greater the acceleration. The larger the change in velocity time, the smaller the acceleration. So you can increase the stopping time, which decreases the acceleration. And if you decrease the stopping time, you can increase the acceleration. And this is, Ava, I'll get to your question in a minute, maybe at the end of this stuff. This is how airbag works in a car. It takes the amount of time your face would normally slow down in, which is by hitting the steering wheel, and it makes it happen in a longer period of time. You hit the airbag, it's a nice cushion, and it slows your face down. So it increases the amount of time it would take your face to run into the steering wheel. And that decreases the acceleration, which increases your chances of surviving, keeping your wonderful face intact. So this is how airbags work, the sort of the principle of airbags. Distance versus time graphs with acceleration and lines of best fit. I wanted to talk about a line of best fit, but I didn't get to it last day. So let's do that now. All right. 2 or 3 things. Line of best fit. When you do an experiment, you're going to get some data. Let's say we were trying to find your position as a function of time. So this is distance versus time graph still. And let's say I said, okay, at 0 seconds, you're at 0 meters. At 1 second, you were at 1 meter. At 2 seconds, you were at 1.9 meters. At 3 seconds, you were maybe here. And at 5 seconds, you were up there. Now, these are all discrete points, meaning they're all individual points. A line of best fit is a way to average your data out. So if I were to draw a line of best fit with these points, I would try to draw a line that went through as many points as possible. I repeat, I do not want to connect the dots. In Physics 11, we don't connect the dots ever. Bad, 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 bad. Same with Science 10. Don't connect the dots. A line of best fit is going to be a line that hits as many points as I can, and the other thing is it should have as many points above the line as it does below the line. So in this case, I'm probably not going to be able to go through all of these points. I'm going to draw a red line here. There's a red line. I'm going to draw a blue line. And maybe draw... I'll just leave those two. Which one's better, the red line or the blue line, and why? It's kind of one of these really basic sorts of ideas. 2 lines I've drawn, they both kind of represent the data. One is maybe a bit better than the other. So I can't go through all of these points with a straight line. If I look at the red line goes through 1 point here, and it goes through another point here. So it's going through 2 points. My blue line is going through 1 point here and 2 points here. It's going through 2 lines. My red line has 1 point below the line, red, and another point below the line. So I have 2 points below my line. How many points do I have above the line? Up here, I have none. So because I have these 2 points, this guy here and this guy here, below the line, that's not a very good line of best fit, the red one. And it's not good because I have 2 points below my line. Whereas if I look at just the blue line here, I'm going through
I'm just missing that one, but pretty close. I've hit 3 points, more or less, and I have 1 point below and 1 point above. So the blue line would be a good line of best fit because it goes through as many points as possible, and you end up with points above and below. That's kind of what a line of best fit is. Sometimes you'll end up with a situation like this, where you have, I'm just going to draw a second, get all these points in a really great line, and then you end up with some goofy point that doesn't fit on the line. And this is a way to account for error in our calculations. It's going to be really hard to draw this. I don't have a ruler, but I'll do my best. So it's a straight line that accounts for as many as possible. This 1 point is probably a mistake. I maybe didn't make a good recording on my ruler or something like that. It's an outlier, which is fine. It happens. That's why we do experiments, to try to get an average. So a line of best fit for that second example, that would be fine. Basically, when you are taking recordings and measurements, your points are going to be all over the place because there's error. You're reading a ruler, you're measuring time, did you press the stop at the right time? And a graph is a great way to kind of eliminate some of the error as a result of your missed sort of calculations. All right. The actual point I wanted to show you here, the reason I showed you these two examples is because on provincial exams and in the curriculum, it says you need to know what a line of best fit. And it's just kind of, I've seen questions on provincials that look like, this. And they show you a bunch of different lines on graphs and they say, which one's the best fit line? And you need to pick the best one. So, 2 questions here I'm getting at. How should the best fit line have as many points going through in equal amounts on either side, or can there be more on one side than the other? There can be more on one side or the other. Imagine if I had another point, maybe right there. Now I have 1, 2 above the line and 1 below the line. If it still looks like a line of best fit, that's fine. You can end up with 1 or 2 below the line. Just like here, I have 1 below the line and 0 above the line. That's fine. There's no rule that says there has to be as many above as below. You want to go through as many as you can and kind of average out your data. And there's no rule that says you have to go through the origin. If you had a scenario like this, where these are your points, and you wanted to draw a line of best fit through that, you don't have to go through the first point. There's no rule that says the first point is more important than all of the other points. Go through the first point. No, you don't have to. So the first point is no more important than that point there. So lines of best fit don't necessarily need to go through the first point. Sometimes we think that they do. They don't. Another question. So even if it isn't uniform motion, do you do a curved line? This is what we want to talk about. This is why I had these graphs. Distance versus time graphs. For accelerated motion, yes, those are GIFs, and there will be a GIF on your test in the physics unit for sure. Distance time graph. Now, on a distance time graph, if I had something that was traveling at a constant velocity, it would be a line like that. What if my object is speeding up? So imagine I have an object that's going at a constant velocity, and then it goes a little bit faster. Now I have a steeper slope, and then a little bit faster. What we end up with, if an object is speeding up, instead of having a straight line, you're going to have a curved line. So let's imagine an object, it's not moving. It's not changing its position at all. Its position is stationary with respect to time. And then it starts to go really slowly. So I have a positive slope. And then maybe it goes a little bit faster. I have a steeper slope. And then it goes even faster. And then maybe it stops moving again. Maybe it starts to slow down. And then it stops moving. So on a position time graph, if I end up with, now imagine this is a nice curved line instead of these small straight lines. If I have a curved line on a position time graph, that means acceleration. As soon as I have a curved line on a position time graph, that means the object's changing its velocity and it's accelerating. The object, you would end up with an object with a constant slope like that, Alex, because terminal velocity means that the velocity isn't changing. So that means the slope isn't changing. The slope of a position time graph is your terminal velocity. So again, getting back to the idea where the object moving in real life doesn't look like anything on a graph. We can't translate an object's movement in the real world to a graph directly, just because it's reached a constant velocity. Just be like you driving in your car going 100 kilometers an hour. Well, you've reached 100 kilometers an hour, your velocity is not changing, it's going to be a straight line. So anytime you see a curved line on a position time graph, that means the object's accelerating, speeding up, or slowing down. One thing that we can do is draw something called a tangent line. So if I wanted to know how fast the object was going at 2 seconds, I would go up, I would find that point. Now I need to take the slope of a line that only has 1 point. So what I can do is I can draw a line that only touches the graph at 1 point. That is called a tangent line. Now, the Learning Guide makes a big fuss about tangent lines. Tangent lines are an idea that are introducing a calculus topic, essentially. And you'll talk about them in Math 11 and calculus. They're not a big part of Science 10, but they do kind of help you understand what's going on. So if I wanted to figure out how fast the object was going and I only have 1 point to deal with, because it's a curved line, I can take what I call a tangent line, find the slope, and that will give us the velocity. All right, I'm going to continue on here. So we drew some graphs. Example 2, how can you tell easily if there's acceleration on a distance versus time graph? You have a curved line. There's another example. The velocity getting bigger or smaller, what is the velocity at the end of the trip? So this gets back to this idea, we talked about tangent lines in Math 10. I don't even remember that. It seems so long ago. Is the velocity of this graph getting smaller or larger? What do we think? Remember, the velocity of a distance time graph is the slope. So is my slope increasing or decreasing? Is my object speeding up or slowing down? If I were to look right here at this portion of the graph, that's a steep slope. Then I were to look right here, that's less steep. And then if I were to look right here, that's even less. And then right here, this bit is horizontal, which means it's not moving. So because my slope is becoming less and less, this object is slowing down. Or has negative acceleration. Okay, let's look at some more examples. Consider this distance versus time graph. Is the velocity getting bigger or smaller? What is the velocity? Graph doesn't go through the origin. What does this tell you? So this is kind of the opposite. I have a very low velocity, and then if you think about drawing tangent lines, the slope is increasing. Means speeding up. And the velocity at the start of the trip. So I'm starting here. It doesn't go through the origin, which is where the axes intersect. What does that mean? Well, it just means I've started to the right of some object. So I'm not starting at the object. So the famous example I've been doing is a tree. It just means I've started my trip just to the right of the tree. Here's my little car. So I haven't started at the tree, I've just started, 2 meters to the right of the tree. And then I'm speeding up. Zoom. All right, now I'm gonna mess with your brains a little bit. Considering the distance time graph, is the velocity getting bigger, smaller, and what is the velocity at the start of the trip? So I think about my slope here, so I have almost zero slope. Then it gets steeper and then steeper, but my slope is negative. And it's getting larger. In terms of a negative. So what does that mean? Well, in this case, I'm just speeding up, but I'm going backwards. My slope's getting larger. It's getting more steep, but it's negative. So speeding up, going backwards. All right, I'll just talk about this velocity versus time graph and a couple important points, and then I'll leave you guys for the day. There are a few more slides that just have additional problems, but I'll go through a bunch of problems with you guys next day. We'll have some time for sure. So we've talked about distance time graphs, and I warned you that we'd get to a point where velocity time graphs appear just as often as position time graphs, and now we're at that point. So the velocity time graph is different than a position time graph. Don't think that they're the same. Don't think that they're showing you the same information, because they're not. If they were, we would just have one. So the motion of an object with changing velocity, an object that's accelerating, its velocity is increasing or decreasing, it's changing its velocity. On a velocity time graph, it isn't a curved line like it was on a position time graph. On a velocity time graph, the way we describe acceleration is say, okay, at 0 seconds, you're traveling at 0 meters per second. Can't see these numbers. At 1 second, you're traveling at 12 meters per second if I go across. At 2 seconds, you're traveling at 25 meters per second. At 3 seconds, you're going 37 meters per second. At 4 seconds, you're going 50 meters per second. So this object is accelerating. It's increasing its speed. And on a velocity time graph, that is just a straight line. If this were a distance time graph, if I change this axis to a D, and I wanted to show the same motion, I could, but it would look something like this. I would have 0, and then it would be doing this kind of increasing velocity if it were a distance time graph. But it's not. It's a velocity time graph. The slope of a distance time graph was velocity. The slope of an acceleration time graph, the slope of a velocity time graph is acceleration. So if you are asked to find the acceleration from a velocity time graph, you need to find the slope. And what if it started accelerating faster? Then if its acceleration was changing, you would see a steeper slope. And that's a completely sort of plausible thing for physics 11, but in physics in grade 10, you'll have things with constant accelerations. It would be a curved line if you were changing your acceleration. That's completely true. So you'd end up with, a steeper slope or a less steep slope if you change your acceleration. We'll start to deal with those sorts of things. You'll never see a curved line on a velocity time graph in Science 10. but you will see lines of different sort of velocities. So if we wanted to find the acceleration of this object, we'd pick 2 points. So you can see these ones have been isolated. 50 minus 25 over 4 minus 2. 25 divided by 2 gives us 13 meters per second squared. Watch your units. Slope is rise over run. Meters per second divided by seconds gives us meters per second squared. Now, I mean, realistically, that's all the nuts and bolts of this stuff. So kind of ran a little bit short on time, and I don't want to take you guys any longer than we need to be here. So that's kind of it. Next class, what's going to look like, I'll see you guys on Tuesday again. We have an hour. I'm going to go through any questions you had from Unit 9. You should be done Unit 8 by the time we make it to next class. Any questions you had from Unit 9? If you guys don't have any questions, I'll finish going through the notes. I think there's like 3 slides left. Just some examples and things like that. So nothing terribly earth-shattering. The next class we have is on Tuesday. And then on Wednesday, we're going to go to KSS at first thing in the morning. So at 8:45, meet me at KSS. We'll do a lab. Be lots of fun. And then I won't see you guys again for till the following week, which is actually the last week of, well, second to last week of class. So from here on out, we're going to finish up Unit 9 next day. We'll have some review material I'll have for you guys, and then we'll just be preparing for the final exam. When would I like this unit in by? I won't see you again until next Tuesday, so if you wanted to bring it to KSS next Wednesday, that would be great. I'll hope that you're done this stuff by Wednesday next week. Test written by the end of next week. So Unit 8 is this week, end of next week's Unit 9. Hopefully that gives you a time frame you can work with. How far in the learning guide can you go? You can do the whole darn thing now. We have covered every topic in the learning guide. What are the common units for displacement? You guys should do that. Some word problems can be a bit tricky. Throw a rock into the air, so objects in free fall. Just kind of positive, negative, circle the one. Graphing with acceleration, you guys should be able to do that. Yeah, you guys are good to go now for the entire Unit 9 learning guide. So finish Unit 8. Once you've done that, finish Unit 9. If you have questions on Unit 9, we'll answer them next day. Next Wednesday, we'll be at KSS. Everyone should be there. It'll be lots of fun. And then we'll just start reviewing. So hopefully that's all right. If you guys run into any problems, send me a message. I'll get back to you. And Abby, I will mark your Unit 8 right now. Thanks, guys. We will see you next week. Bye.